Okay, let's get started, please. So we have finished chapter 3, and we're going to enter the last chapter of the course, which is chapter 7. Sequences and series of functions. Okay, so I tend to skip I generally skip the integration chapter for this chapter. I think this is more valuable material, and the integration chapter is on the Riemann integral. And if you take the graduate real analysis course, you'll actually be introduced to the Lebesgue integral, which is kind of the better version of the Riemann integral. So you learn the Riemann integral, but then you would throw it away almost immediately. So yeah. So in any case, I think it's important to get to this material. So up until now, we've been doing sequence and series of points, right? So we've got points in a metric space, and we talk about the convergence of those points. Now those points are going to be functions. Okay, so each of those points is a function, is a member of some set of functions. You're taking points in a function space, and we're thinking about what does it mean about convergence of these sequences or a series of functions. Okay, so let's start off with one way of talking about convergence of functions. There's actually lots and lots of different ways of talking about what does it mean for functions to converge to, what does it mean for a sequence of functions to converge to some function. You could think of actually many different ways of talking about this. But one simple way is the following. So it's called pointwise convergence. So you have some subset of a metric space. So E is a subset of X. X is a metric space, and you have a sequence of functions on E. Okay. Sequence of functions. Okay. So each of these functions is complex valued, right? You've got some space, right? You've got some metric space, X, and you've got some subset, E sitting inside of it, and then you've got these functions, and these are all maps to the complex plane. Okay, they're all complex valued functions on E. Okay, and the definition is the following: if the limit of f of n, x as n goes to infinity, exists for each x and E, and call that limit f of x, then we say that Fn converges pointwise to f on E. Okay, and kind of as you expect, right? If the sum of the f sub n x converges for all x and E, then we can define the sum of the series, right? F of x as whatever those limits are. Okay, so we can talk about series, sums of functions. We can talk about sequences of functions, and we can talk about series of functions, as you might expect. Okay, so this is kind of what you would, maybe if somebody asked you, what does it mean for a bunch of functions to converge, this is probably what you would come up with. Let me give you some examples to make this concrete. So you can have some function. Let's say we're looking on the interval 0, 1, and we're looking at real valued functions. They just, where f sub n of x is x to the n. Okay, so right, here's the graph. Here's the graph. Here's 0, 1, right? And of course, the f1 is just going to be x, right? F1 is going to look like this. F2 is the x squared, right? Is x squared. F3 is x cubed, right? F4 is x to the fourth, and so on and so forth. Okay, so these are a bunch of functions, right? Here's the first one, f1. Here's the second one, f2. The third one, f3, f4, etc., etc. Right? So you got these functions, and they converge. These functions, the s of n, converge pointwise to some function f. Okay, so I want you to take 30 seconds and tell me figure out what the limit is, what the pointwise limit is of this sequence. Okay, so the pointwise limit, the way you get the pointwise limit is you say, well, we're going to look at each point in our domain, and then see what the limit is as n goes to infinity. Okay. So, and then we'll call that thing, the limit f, the limit function f at x. So take each x and see what happens, and define your f in that way. Okay, turn to somebody nearby and talk with them about what you think the limit is.
So I take the vertical line. Every time that n increases, it's small. You can prove that say x is n plus 1. Or you can hit the left hand side.
Okay. Does somebody want to tell me what the pointwise limit is? What's the pointwise limit of this function? Right. So you want to see what happens at every point, right? What happens at each point? Well, who has an answer? What is f? Right. So let's let f denote the limit. Right. F is going to be this limit function, pointwise limit. You fix each point and then take the limit as n goes to infinity. Dylan.
I think it's 0 or less than 1.
0 for less than 1? Okay.
Yeah, because you just take a smaller ratio.
Sure.
That's less than 1. And
Okay.
you keep multiplying, eventually you're 0.
Okay.
That's what I think.
So what's the function then? So what does the function look like? Is it 0? So here's my domain 0, 1. And you're saying it's a 0 function?
At 1, it's 1.
At 1, it's 1. Okay, yeah. So, yeah, that's right. I hope everybody got that, right? I saw some fist bumps going on. I hope you're still you're still happy with yourselves. Okay, so yeah, right, because at every point, right, for x, right, for x less than 1, right, we're going to have the limit of x to the n as n goes to infinity, right? For x less than 1, that's going to be 0, right? Right, but for x equal to 1, that's going to be 1, right? So the point at, at each point x, right, you see that the values, if you're less than 1, the values are all going to be dropping towards to 0. Right? And then at 1, of course, all the values just stay at 1 and stay there. Okay, so that's the pointwise limit. Okay, so this is, I think this is maybe what you would think the limit of a function, limit of a sequence of functions ought to be, right? If I asked you how should we define it, this is probably how you would define it. You'd say, well, we're going to look at every point and see what the sequence of those. We'll look at the sequence, right? We'll fix the point, right? And then we'll look at this. We'll look at the sequence, right? And then we know all about sequences already. We'll just look at let n go to infinity and call that thing the limit function. Okay. Okay. So one thing to note is that these guys are continuous, but this thing is discontinuous, right? The limit is actually discontinuous. So you've got a bunch of these things converge. These things converge you have a bunch of continuous functions that converge pointwise to a discontinuous function. Okay, and that actually is something that you might not want to happen. Okay, let me give another example. Okay, so my second example, and it's actually not really an example, but the second example is what I'm going to call blimp functions. This is how they were described to me many, many years ago by a cool professor. Again, we're on 0, 1, okay, and the way that you define the functions are like this. So the first function it takes the value 1 all the time. Okay, so that's f1. Okay, the second function f2. This is the blimp. Okay, and the blimp covers the whole world in this case. Okay. Now the second blimp is only half as long as is only length a half. Okay, and it only covers from 0 to half, and there's no blimp after that. Okay, so it is it takes on the value 1 from 0 to a half, and then 0 after that. Okay, the third function starts where the second function ended. And is only length 1/3 this time. Okay, and it's 0 everywhere else. Okay, the fourth blimp is length 1/4, right? And it starts where the third blimp ended, right? And so on and so forth, with a wraparound. Okay, so that if you get to the end here, and you will, because what's the sum of 1 plus a half plus a third plus a fourth? What's 1/2 plus a third plus? It's infinite, right? We saw that's the harmonic series which diverges, right? So these blimps are going to be they're going to be going. There's going to be one here, there's one here, one here, and it starts wrapping around. They get smaller and smaller, but they keep on going, right? Right. So okay, so there's some wraparound, just like in a video game where you run out this right side and you come back in on the left side. Okay. Okay. So so those are my functions. F1, F2, F3, and so on and so forth. What is the pointwise limit? This is a trick question. Is there a pointwise limit? Again, think about it for half a minute, and then I'll have you talk with each other. Okay, talk with each other, please. Okay, anybody want to tell me if there is a pointwise limit, and if there is, what it is? Is there a pointwise limit? No, there's some shaking heads. Why not? Why not? I guess I sort of gave you the answer already. Right. The answer is what causes there not to be a pointwise limit? Yes, go ahead.
Because there's wraparound, by the time, like, there will exist a point, like, for any given n, there will exist a point where it's 1,
Yeah.
and then 0. And it's always 0 and then the 1, it wraps around.
That's right, that's right. So the point is that the total length of these blimps is infinite, right? That's actually the point, right? That the sum of the lengths of these blimps is infinite. So, right, it may be that you have to wait a long time for a blimp to come by, but there will be infinitely many of them coming by, right? So you'll be sitting there, right? So suppose you're at this point here, right? This is you're looking up, you see the first blimp, you see the second blimp, and then you wait for a while, and then I'm not sure which blimp you'll see, but eventually one's going to come by, and since the sum of although they're shrinking in length, the total of their lengths is infinite. So you know that there's going to be infinitely many blimps passing above you at some point. Right. So for each x, your sequence is going to look like one. It'll start off kind of frequent, and then become logarithmically infrequent. Right. So right. But you're still going to see them. Okay. So this does not converge pointwise. Does not converge pointwise. Okay, this sequence does not converge pointwise, but you kind of think that by the time you get to the millionth blimp, right? What does your function look like? Well, it's going to be 1 on an interval of length 1 millionth, right? And 0 everywhere else. Right? By the time you get to a billion, for most of the time, your function is going to be the 0 function, right? So you think this ought to be convergence to the 0 function, right? And there's a kind of convergence that we're not going to talk about, but you'll see in 137. That's called convergence in measure. Convergence in measure, and the blimp functions converge to the 0 function in measure, although they don't converge pointwise. Okay, so I'm just going to give a bunch of sort of examples of things that converge and things that aren't really aren't as nice as we would like them to be. Okay, so the first example was this one where we've got continuous functions And they converge pointwise, but they converge to something discontinuous. Okay. So here's here's an example. Fnx is 1 over the square root of n sine nx for n equals 1, 2, 3, etc. And the derivative, if you take the derivative, is the square root of n times the cosine of nx. Okay, again, of course, 1, 2, 3, etc. Okay. Okay. So, what's the limit as n goes? What's the pointwise limit of the f sub n? Can anyone just tell me? Just look at it. What happens as n goes to infinity? 1 over root n.
0.
Yes, very good. It's going to be the 0 function, right? Because this function is trapped between -1 and 1, right? And you're dividing by 1 over root n, which becomes infinitely small. And so the limit of this function is 0, right? So if I take the limit, I get the 0 function. And if I differentiate that, well, I still get the 0 function, right? So if I have the 0, I take the limit and then I differentiate it. Okay, I get the 0 function. Okay. On the other side, I'm going to take the derivatives and then I'll take the limit. Okay, so, right. So what happens there? If I take the derivatives first and then I let n go to infinity, what's the limit? What's the limit over there?
Like oscillates between infinity and infinity?
Well, so one thing that happens is that as n gets big, right, the frequency increases, right? So your function is the oscillation is going to increase, right? More oscillation, right? And then the other thing that happens is that you're multiplying by the square root of n, so the amplitude is also increasing, right? Okay, so as n goes to infinity, well, you don't have a limit, right? There's no limit, so it's no limit. Okay, so this is kind of bad because you would hope that what you would like would be that if you take the limit and then take the derivative, it should be the same thing as you take the derivative and then you take the limit. Okay, but that doesn't happen for pointwise. That doesn't happen for pointwise convergent functions, for pointwise convergent sequences. Okay. Okay, so that's limit, pointwise limit, and differentiation don't commute. And you can't switch the order. Okay. Another example about limit, pointwise limit, and integral. Definite integral. Okay. So here's one example. We'll let f and x be the characteristic function of the interval n plus 1. Okay. So I haven't used this notation before. This is called the characteristic function of a set. Okay, so when I say chi of some set, the notation is this. If I say chi of some set, then that's the function that takes on 1 if x is in the set and 0 if x